Common collections. Rust's standard library includes a number of very useful data structures called collections. Rust's standard library includes a number of very useful data structures uh, called collections. Um, Most other data types represent one specific value, but collections can contain multiple values. Unlike the built-in array and tuple types, the data these collections point to is stored on the heap, uh, which means that the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Each kind of collection has different capabilities and costs, and choosing an appropriate one for your current situation is a skill you will develop over time. In this chapter, we will discuss three collections that are used very often in Rust programs. Which means the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Each kind of collection has a different capabilities and costs, and choosing an appropriate one for your current situation is a skill you will develop over time. Okay. A vector allows you to store a variable number of values next to each other. A string is a collection of characters. A string store a variable number of values next to each other. A string is a collection of characters. String is a collection of characters. We've mentioned the string type previously, but in this chapter we will talk about it in depth. A hash map allows you to associate a value with a particular key. It's a particular implementation of the more general data structure called a map. A hash map allows you to associate a value with a particular key. Okay. It's a particular implementation of the more general data structure called a map. Okay. To learn about the other kinds of collections provided by the standard library, see the documentation. We will discuss how to create and update vectors, strings, and hash maps, as well as what makes each special. Storing lists of values with vectors. The first collection type we will look at is vectee, also known as a vector. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. The first collection type we will look at is vectee, also known as a vector. Vectors allow you to store more than one value in a single data structure. Vectors allow you to store more than one value in a single data structure. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. Vectors can only store values the same type. Vectors can only store values of the same. Okay, they are useful when you have a list of items, such as the lines of text in a file or the prices of the items in a short shopping cart. Creating a new vector. To create a new empty vector, we call the vec new function as shown in listing 8-1. Listing 8-1, creating a new empty vector to hold values of type i32. Note that we added a time annotation here because we aren't inserting any values into this vector. Note that we added a type annotation. Here. We added a type annotation here, okay? Note that we added a type annotation here. Okay. Because we aren't inserting any values into this vector, Rust doesn't know what kind of elements we intend to store. Because we aren't inserting any values into this vector, Rust doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generics. We will cover how to use generics with your own types in chapter 10. For now, know that the vectee type provided by the standard library can hold any type. When we create a vector to hold a specific type, we can specify the type within angle brackets. We can specify the type. We can specify the type within the angle brackets. In listing 8-1, we've told Rust that the vectee in V will hold elements of the I32 type. More often, you will create a vectee with the initial values and Rust will infer the type of value you want to store. So you really need to do this type annotation. Rust conveniently provides the vec macro which will create a new vector that holds the values you give it. Listing 8-2 creates a new vec I32 that holds the values I1, 2, and 3. The integer type is I32 because that's the default integer type. As we discussed in the data type section of chapter 3, let v equals vec123, creating a new vector containing values. Because we've given initial I32 values, Rust can infer that the type of v is vec I32, and the type annotation isn't necessary. Next, we will look at how to modify a vector. Updating a vector. To create a vector and then add elements to it. Updating a vector. To create a vector and then add elements to it, we can use the push method as shown in listing 8-3. Using the push method to add values to a vector. As with any variable, if we want to be able to change each value, we need to make it mutable using the mute keyword, as discussed in chapter 3. The numbers we place inside all of type I32 and Rust infers this from the data, so we don't need the vec I32 annotation. As with any variable, if we want to be able to change its value, we need to make it mutable. As with any variable, if we want to be able to change its value, we need to make it mutable using the mute keyword. As discussed in chapter 3, the numbers we place inside are all of type I32 and Rust infers this from the data. So we don't need the vec I32 annotation. Reading elements of vector. There are two ways. There are two ways. There are two ways to reference a value stored in a vector. There are two ways to reference a value stored in a vector via indexing or using the get method. In the following examples, we've annotated the types of the values that are returned from these functions for extra clarity. In the following examples, we've annotated the types of the values that are returned from these functions for extra clarity. In the following, we'll annotate the types of values that are returned from these functions. Listing 8-4 shows both methods of accessing a value in a vector with indexing syntax and the get method. Okay. Listing 8-4 using indexing syntax or the get method to access an item in a vector. Using indexing syntax. 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 Using indexing syntax or get, okay, indexing. Oh, here's indexing. And then get, okay. Note a few details here. We use the index value of 2 to get the third element because vectors are indexed by number, string 0. Using ampersand and array gives us a reference to the element at the index value. Note a few details here. We use the index value of 2 to get the third element because vectors are indexed by number, starting at 0. Using ampersand and brackets gives us a reference to the element at the index value. Oh, it gives us a reference. Ampersand and brackets gives us a reference to the element at the index value. When we use the get method with the index passed as an argument, we get an option T that we can use with the match. Okay, that makes that's why we are using third here, okay? Some third, mean third. Okay, makes sense. The reason Rust provides these two ways to reference an element is so you can choose how the program behaves when you try to use an index value outside the range of existing elements. As an example, let's see what happens when we have a vector of 5 elements and then we try to access an element at index 100 with each technique, as shown in listing 8-5. Listing 8-5 attempting to access the element at index 100 in a vector containing 5 elements. When we run this code, the first bracket method will cause the program to panic because it references a non-existent element. When we run this code, the first bracket method will cause the program to panic because it references a non-existent element. This method is best used when you want your program to crash if there's an attempt to access an element past the end of the vector. Listing 8-5 attempting to access the element at index 100 in a vector containing 5 elements. Listing 8-5 attempting to access the element at index 100 in a vector containing 5 elements. Listing 8-5 attempting to access the element. Attempting to access the element. Attempting to access the element. We try to access an element at index 100 with each technique, as shown in listing 8-5. Attempting to access the element at index 100 is a vector containing 5 elements. When we run this code, the first bracket method will cause the program to panic because it references a non-existent element. This method is best used when you want your program to crash if there's an attempt to access an element past the end of the vector. When the get method is past an index that is outside the vector, it returns none without panicking. You would use this method if accessing an element beyond the range of the vector may happen occasionally under normal circumstances. Your code will then have logic to handle having either some element or none, as discussed in Chapter 6. Uh, for example, the index could be coming from a person entering a number. If they accidentally enter a number that's too large and the program gets a non-value, you could tell the user how many items are in the current vector. You could tell the user how many items are in the current vector and give them another chance to enter a valid value. That would be more user-friendly than crashing the program due to a typo. When the program has a valid reference, the borrow checker enforces the ownership and borrowing rules. When the program has a valid reference, the borrow checker enforces the ownership and borrowing rules covered in Chapter 4. To ensure this reference and any other references to the content of the vector remain valid. Recall the rule that states you can't have mutable and immutable references in the same scope. That rule applies in listing 8-6, where we hold an immutable reference to the first element in a vector and try to add an element to the end. This program won't work if we also try to refer to that element later in the function. Wait a second. Ensure this reference and any other reference to the instance of the vector remains valid. Recall the rule that states that you can't have immutable and immutable references in the same scope. That rule applies in listing 8-6, where we hold where we hold an immutable reference to the first element in a vector and try to add an element to the end. This program won't work if we also try to refer to that element later in the function. Compiling this code will result in this error. Attempting to add an element to a vector while holding a reference to an item. The code in listing 8-6 might look like it should work. Why should a reference to the first element care about changes at the end of the vector? This error is due to the way vectors work. The code in listing 8-6, okay, might look like it should work. It might look like it should work. Why should a reference to the first element? Why should a reference to the first element care about changes at the end of the vector? Why should a reference to the first element? Why should a reference to the first element? Why should a reference to the first element care about changes at the end of the vector? Why should a reference to the first element care about changes at it? Oh, immutable borrow occurs here, and the immutable borrow occurs here. Ah. The coding should look like it should work. Why should a reference to the first element care about changes at the end of the vector? This error is due to the way vectors work. This error is due to the way vectors work. Because vectors put the values next to each other in memory. Because vectors put the values. Because the vectors put the values. Because the vectors. Because the vectors put the values. Because put the vectors. Because vectors put their values. Because vectors put the values next to each other in memory. Because vectors put the values next to each other in memory, adding a new element onto the end of the vector might require allocating new memory and copying the old elements to the new space. And copying the old elements to the new space. End of the vector might require allocating a new memory. Adding a new element onto the end of the vector might require allocating a new memory and copying the old elements to the new space. If there isn't enough room to put all the elements next to each other where the vector is currently stored. Next to other where the vector is currently stored. In that case, the reference to the first element would be pointing to deallocated memory. If there isn't enough room to put all the elements next to each other where the vector is currently stored. In that case, the reference to the first element would be pointing to deallocated memory. The borrowing rules prevent the programs from ending up. The borrowing rules prevent programs from ending up in that situation. The borrowing rules prevent programs from ending up in that situation. Iterating over the values in a vector. If there isn't enough room to put all the elements next to each other where the vector is currently stored, in that case, the reference to the first element would be pointing to deallocated memory. The borrowing rules prevent the programs from ending up in the system. If there isn't enough room to put all the vectors together, in that case, the reference to the first element would be pointing to be deallocated. Oh, this is already pointing to the reference here. They're pushing. Okay, makes sense. The borrowing rules prevent the programs from ending up in this situation. Makes sense. For more on the implementation details of the vec type, see iterating over the values in vector. Iterating over the values in a vector to access each element in a vector in turn. We would iterate through all of the elements rather than using these indices to access one at a time. Listing 8-7 shows how to use a for loop to get immutable references to each element in a vector of i32 values and print them. To access each element in a vector in turn. To access each element in a vector. To access each element in a vector in turn, we would iterate through all of the elements rather than use indices to access one at a time. Listing 8-7 shows how to use a for loop to get immutable reference to each element in a vector of i32 values printed. Access each element in a vector in turn, we would iterate through all of the elements rather than use indices to access one at a time. To access each element in a vector in turn. To access each element. To access each element in a vector in turn. To access each element in a vector. To access each element in a vector in turn, we would iterate through all of the elements rather than use indices to access one at a time. Listing 8-7 shows how to use your for loop to get immutable reference to each element in a vector of i32 values and printed. Printing each element in a vector by iterating over the elements using a for loop. We can also iterate over immutable references to each element in a mutable vector in order to make changes to all the elements. The full loop in listing 8-8 will add 50 to each element. To change the value that the mutable reference refers to, we have to use asterisk the reference operator to get the value in I before we can use plus equals operator. We will talk more about the dereference operator in the following pointer to the value with the dereference operator section of chapter 15. We can also iterate over mutable references. We can also iterate over mutable references. We can also iterate over mutable references to each element. We can also iterate over mutable references. Iterate over mutable references to each element of the vector. To change the value that the mutable reference that we have to the change the value that the mutable reference refers to. So free, so fine. This is the reference. We should do the reference here. Iterating over a vector, whether iterating over a vector, whether immutable or mutably is safe because of the borrow checkers rule. Iterating over a vector, whether immutably iterating over a vector. Okay. If we attempted to insert or remove items in the full loop bodies in listing 8-7 and listing 8-8, we would get a compiler error similar to the one we got with the code in listing 8-6. The reference to the vector that the full loop holds prevents the simultaneous modification of the whole vector. Using an enum to store multiple types. Vectors can only store values that are the same type. Using an enum to store multiple types. Vectors can only store values that are the same type. This can be inconvenient. There are definitely use cases for needing to store a list of items of different types. Fortunately, the variants of an enum are defined under the same enum type. So when we need one type to represent elements of different types, we can define and use an enum. For example, say we wanna get values from a row in a spreadsheet in which some of the columns in the row contain integers, some floating point numbers, and some strings. We can define an enum whose variants will hold the different value types, and all the enum variants will be considered the same type, that of the enum. Then we can create a vector to hold that enum and so ultimately hold its different types. We will demonstrate this in listing 8-9. Defining an enum to store values of different types in one vector. Rust needs to know what types will be in the vector at compile time so it knows exactly how much memory on the heap will be needed to store each element. Wait a second. For example, say we wanna get values from a row in a spreadsheet in which some of the columns in the row contain integers, some floating point numbers, some string. We can define an enum whose variance. We can define an enum whose variance will hold the different value types and all the enum variants will be considered the same type. We can define an enum whose variance will hold the different value types. We can define an enum whose variance will hold the different value types, and all the enum variants will be considered the same type, that of the enum, that we can create a vector to hold that enum, and so ultimately hold these different types. We've demonstrated this in lesson 8-9. Rust needs to know what types will be in the vector at compile time, so it knows exactly how much memory on the heap will be needed to store each element. We must also be explicit about what types are allowed in this vector. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on the elements of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that every possible case is handled. As discussed in chapter 6, if you don't know the exhaustive set of types a program will get at runtime to store in a vector, the enum technique won't work. Instead, you can use a trait object, which we will cover in chapter 17. Now that we've discussed some of the most common ways to use vectors, be sure to review the API documentation for all the many useful methods defined on vect by the standard library. For example, in addition to push, a pop method removes and returns the last element. Rust needs to know what types will be in the vector. Rust needs to know. Rust needs to know what types will be in the vector. Rust needs to know what types will be in the vector at compile time. Rust needs to know what types will be in the vector at compile time, so it knows exactly how much memory. Rust needs to know what types will be in the vector. Rust needs to know what types will be in the vector at compile time. Rust needs to know what types. Rust needs to know what types will be in the vector. Rust needs to know what types will be in a vector. Rust needs to know what types. Rust needs to know what types will be in the vector at compile time. Rust needs to know what types will be in the vector. Rust needs to know what types will be in the vector at compile time. Rust needs to know what types will be in the vector at compile time, so it knows exactly how much memory on the heap will be needed to store each element. We must also be explicit about what types are allowed in this vector. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on elements of vector. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on the elements of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that every possible case is handled. as discussed in chapter 6. Using an enum plus a match expression means that Rust will ensure that compiled. Okay. If you don't know that exhaustive set of types a program will get at runtime to store in a vector, the enum technique won't work. If you don't know the exhaustive set of types, if you don't know the exhaustive set of types, if you don't know the exhaustive set of types, types, a program will get a runtime to store the program will get at runtime to store in vector. The enum technique won't work. Instead, you can use a trait object, which we will cover in chapter 17. Now that we've discussed some of the most common ways to use the vectors, be sure to review the API documentation for all the many useful methods defined on vectee by the standard library. For example, in addition to push, a pop method removes and returns the last element. Dropping a vector drops its elements. Like any other structure, a vector is freed when it goes out of scope, as annotated in Listing 8-10. Like any other struct, a vector is freed when it goes out of scope. Like any other struct, a vector is freed when it goes out of scope, as annotated in Listing 8-10. Do service v goes out of scope. Okay, makes sense. Oh, vector is freed when it goes out of scope, as annotated. When the vector gets dropped, all of its contents are also dropped, meaning the integers it holds will be cleaned up. The borrow checker ensures that any references to contents of a vector are only used while the vector itself is valid. Let's move on to the next collection type string. When the vector gets dropped, all of its contents are also dropped, meaning the integers it holds will be cleaned up. The borrow checker ensures that any references to contents. The borrow checker ensures that any references to contents of a vector are only used while the vector itself is valid. Parsec ensures that any reference to contents of vector only used while the vector is valid. Okay, makes sense. That makes sense. Which call to this find until function will cause a runtime panic. Which call to this find function will runtime find until we back okay, and then what the fuck is I don't know. Till okay. I vi equals n. I equals n. Oh, vi equals n. Okay. Okay. Yeah, makes sense. One, two, three, 0, 0, 0, 0. 1, 2, 3, 3, 3. I in 0, 3. Ah, 1, 2, 3. Makes sense. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, and oh, to side 4 here. 4, 4 ships here. 4, 1, 2, 3. 0, 1, 2. Oh, oh, fuck. 0, 1, 2, 3. What the heck? Zero, 1, 2. 0, 1, 2. Till till 4. Shit. Jesus Christ. Oh, so 1, so 1, okay, 1 and find 1, yes. And 3. So this is 3, 3, and 3. So here 3, and then 0, 1, 2, 3, and oh, second. Wait a second. So 0, 1, 0, 0. Doesn't make sense. Yeah, it's just not. And then 1, 2, 3. 3, 3, 3, 3. 0, 1, 2, 3, 0, 1, 2. Oh. And then 0, 1, 2, 3. 1, 2, 3. So 4, 4, 4, and 1, 4. So 1, 4, 1, 2, 2, 3, 4, 4. 2, 4, 4. But it going 1, 2, 3, and 4, 4. Complex compile. Mute v 1, 2, 3. Mute v push it. This program was in second. Wait 3 v 4 5. 1, 2, 3. 1, 2, 3. Mute v. Okay. And I. Oh, what? What? Oh shit. Factory 1, 2, 3. And then 1, 2, 3. 1, 2, 1, 1, 2, 3. 1, 0, 1, 2, 3, 4, 5. Shit. Factory new string from hello pushes that pushes the world original as okay, but this is not mutable. So I think it does not combine because of this here 5. 3, 1, 2, 3, value new 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Stacy Cloud. 3, 3, 2, 0, 5. 3, 2, mutable. 1, 1. The reason is with 2 equals 5, it cracks. It cracks. Go here. Shit. Oh my god. Ah, Jesus Christ. This program does not compile the error occurs to line number 4. Even though v is immutably borrowed, this that only allows I to be mutated. I to be mutated inside the for loop. Not wait. What? Even though v is mutably borrowed. Even though v is mutably borrowed. Even though v is mutably borrowed. V is mutably borrowed. V is mutably borrowed. Even though v is mutably borrowed. That only allows I to be mutated inside the for loop. Therefore, calling v dot push is an ownership matter. What? Mute. Mute free. Oh, Jesus, difficult. This program does not compile. The error occurs on the line number 6. Ah, shit. Push is here. That push moves its argument. Push moves with push moves its argument, so it should not be left to recalling with push. So it's just negative after calling with. Therefore, calling println is not ownership safe. Determine whether a programmer passes the compiler. If it passes right, what will happen? But this means that if an input original S, and so this is also possible. Interesting. Very interesting. It is possible. Determine whether the programmer passes Dash does it compile the output of this program will be 55. is time width I32. Then with I32, meaning it is a pointer to a number within V. So if we push I into V2, we push I into V2, then V2 contains the pointers to V. Oh, okay, fine. So then the reference.